Hi guys, this is review 2 homework and question number 2 in that homework. So you're gonna have a cylinder falling down, rolling down of an incline, and the angle in between the incline and the table is 30 degrees, and that's also on a table, and the height of a table is 0.75. It's going to go down and it's going to travel distance d on the horizontal, and the mass of the cylinder is 0.5 kilograms, and the radius of that cylinder is 0.1 m. And moment of inertia of the cylinder is given as mr squared over 2. So once you plug in all of the numbers, m for 0.5 and r as 0.1 and square and divide it, then you're going to find your moment of inertia as 0.0025. We are going to use that in the later on. So in the first part, they are basically asking for the kinetic energy of the cylinder as it reaches to the horizontal table. So it's going to go down from this point to this point. So to be able to figure that out, we basically use the conservation of energy. So it doesn't matter if it rolls or not, because it's asking for total kinetic energy. It doesn't specify linear or kinetic. So all we need to say is total mechanical energy is the same at all points, and you took top point and the bottom point, and then the top, it starts from rest, so the only energy that it has is gravitational potential, which is mgh, and in the bottom it's going to have both rotational and transitional kinetic energy, but we don't need to specify because they're asking for total kinetic energy, so it's just kinetic energy. And what is a way for us to calculate the potential energy? It's mgh, m is 0.5, g is 10, and height. How do you find this height? So if you think about it, the hypotenuse is given as 1 meters, and then the angle is given as 30. So 30 is the across of, or this height is the across of 30, so that we're going to use sine 30 basically. And sine 30 times 1 is going to be 0.5, because sine 30 itself is 0.5. So once you multiply all of those numbers, you'll be able to figure out the kinetic energy of that cylinder at the bottom or on the table. And that's going to be 2.5 joules. And in part B, they are specifically asking for angular velocity of the cylinder. So now in this case, we need to specify as rotational and transitional, because we're going to have the omega in the rotational part, and we will use the transitional part, but since they're asking for omega, we need to write this transitional kinetic energy in terms of rotational quantities. So let's write it down. I basically switched them. So 1/2 mv squared is my transitional kinetic energy, and 1/2 I omega squared is my rotational kinetic energy. But since they're asking for omega, then I need to convert that v into the rotational terms, and v is going to be r times omega. So all we need to do is write down all of the quantities and then solve the equation for omega. So it's just a long math over here. There's not much of a difficulty here, it's just long math. So you just need to be careful with the numbers. So my kinetic energy, total kinetic energy is 2.5, and then 1/2, and my mass is 0.5, and my v is going to be replaced with r omega. So r is 0.1, omega is omega, and that's what we're trying to figure out, and square, plus 1/2 I. Remember, we find it over there as 0.0025. We replace it times omega squared. And then you do the math. You got this 0.0025 omega squared plus 0.002125 omega squared. So you have that many omega squared and that many omega squared. You just add them together. And at the end, you're going to have 0.00375 omega squared. And if you divide both sides with 0.0375, then you find omega squared as 667 roughly. And once you take the square root of both sides, then you find your omega as 25.8 radians per second. And in part C, they are asking for the ratio of the total kinetic energy at the bottom, all right, on the floor. That's important. They're not asking for this part, but they're asking for the floor and the ratio of that total energy in the bottom to on the floor and the rotational kinetic energy of the disk. So what's going to happen is it's still going to go with 1/2 I omega squared, and what's going to happen, this is the rotational kinetic energy, but your kinetic energy, total kinetic energy, same idea over here, but instead of going from this height, we will just convert that kinetic energy, because the only energy that you have on the top is gravitational potential energy, and all of that will be converted to kinetic at the bottom. But this time, instead of using just mgh, instead of converting from this point to this point, we're going to convert all of it. So we're going to go all the way from top to all the way bottom. So your mgh in this case is going to be 0.5 times 10 plus 0.75, which is the height of the table, plus the h, which is the height of the incline. And we found already over here previously sine 30 times 1, which is 0.5. So 0.5 plus 7.75 is 125. And once you do the math over here, you're going to find it as 625. And your rotational kinetic energy that we found is basically 1/2 omega squared. And we found over here previously. And I was already constant, so once you do the math over here again, you find it as 0.85, and whenever you get the ratio, then you find this as 0.85, 0.13. And in part D, they are this time asking for the distance that it's going to travel once it leaves the table, and that's simply motion in 2 dimensions, and you should remember that the height of a free-falling object is equal to 1/2 gt squared. So the height that we fall is 0.75, 1/2, and rg is just 10, and t squared. So whenever you put all the numbers, then you will find that t equals 0.39 seconds. And after this, we are going to need, to be able to find the distance d, we know that it's horizontal velocity times time. And my horizontal velocity at this point is basically my rotational, like angular velocity times r at that point. And we calculated this omega at the bottom at this point as 25.8. So once you multiply it with the radius of it, then you're going to be able to find the linear velocity of that cylinder at that point. So that would be the horizontal velocity of it. So if you multiply with this horizontal velocity with the time, then you're going to be able to find the distance. And once you multiply all those numbers, you will find that it's pretty close to 1. And it's just basically 1 meters. And in the last part, there are some conceptual questions. So instead of having a cylinder, now you are going to have a sphere. And the moment of inertia of the sphere is not 1/2, but it is 2/5 mr squared. So if you think about it, 1/2 mr squared is like 0.5. And 2/5 is basically 0.4 mr squared. So your new moment of inertia is less than your old moment of inertia. In the first part, they are basically asking for total kinetic energy on the floor. And remember, total kinetic energy depends on your, basically, like from conservation of energy, your potential energy on the top. And since mass is not important, and since both are released from the same location, they are basically going to have the same kinetic energy at the bottom as well. So both has the same initial gravitational potential energy, so they will both have the same kinetic energy due to conservation of energy. But again, this is the total one, not rotational, not kinetic. This is the total. So in part 2, they are now asking for rotational kinetic energy. So we know that total kinetic energy will be the same, but what will happen to the rotational kinetic energy? So instead of writing them down, I just put like the relationships and then let's see how it goes. So moment of inertia of this sphere is less than the cylinder. So if moment of inertia is less, that means you're going to have less resistance to the movement. That means your velocity, your linear velocity, will be more than your the velocity of the sphere will be more than the velocity of the cylinder. So velocity is more, but what do we know about the mass? It's the same mass. So masses are the same. So in this case, what are we going to conclude? The transitional kinetic energy of the sphere is greater than transitional kinetic energy of the cylinder. But what did we know in the previous part? Total kinetic energy is the same for both. So if the same, like the total is the same, and transitional kinetic energy of the sphere is more, then the rotational kinetic energy of that sphere will be less than the cylinder. And in the last part, they're asking for what will be the distance that is going to travel. So distance is related with v and t. They both fall down from the same distance, 0.75. So time will be the same for both. And since sphere is going to have more linear velocity at the moment, then it is going to go farther distance than cylinder. And this is your solution for question number 2 on your review packet 2.